In this video, we're going to describe chemical bonding and chemical structure. For example, if we look at a water molecule, we can think about the chemical interaction that occurs between the oxygen atom and both hydrogen atoms, such that the hydrogen atom and oxygen atom make a chemical bond that connects these two particular atoms. We can also think about the geometrical structure of the overall molecule. For example, we happen to know that the angle that forms between the hydrogen atom, oxygen atom, and hydrogen atom in water is about 104.5 degrees. So that's a description of its geometrical structure. And in this video, we're going to begin thinking about bonding and structure and how we can go about doing so. The first thing that we're going to need to learn about in order to begin our study of bonding and structure is something called Lewis electron dot symbols. And Lewis electron dot symbols are very helpful in allowing us to look at the bonding and structure in molecules. And very simply put, all one needs to do to draw a Lewis electron dot symbol is take the symbol for an atom. Like let's say we want to draw it for hydrogen. So I'm just going to draw the symbol for hydrogen. And then next to the atom we place a dot or an X that represents the number of valence electrons that atom has. Well, hydrogen just has one electron, and its electron is in its valence shell, so I can just put an X here, and this is very simply the Lewis electron dot symbol for hydrogen. If I wanted to do this, say, for fluorine, all the way here on the other side, well, that's going to be, let's see, 1, 2, skip a few, 3, 4, 5, 6, 7. All of the halogens have 7 valence electrons, so if I wanted to draw the Lewis electron dot symbol for fluorine, I would put 1, 2, 3, 4, 5, 6, 7 valence electrons around the symbol for fluorine. Now what we can begin to see is how these atoms share valence electrons in order to form chemical bonds. And when this is done, when atoms share electrons to form a bond, we call them covalent bonds. And I can kind of see the word cooperate in the name. Cooperating valences. Cooperating valence electrons make a bond. So the simplest case of this is a hydrogen atom and another hydrogen atom. Notice I've drawn the Lewis electron dot symbols for both hydrogen atoms. And if we think about the electronic configuration of each hydrogen atom, so this represents the electronic configuration of this particular hydrogen atom, and this represents the electronic configuration of this particular hydrogen atom. What we see is that if this hydrogen atom gains an electron, well, that's going to fill the 1s subshell, and in fact, it's going to fill the entire first shell. The same is true, of course, for this hydrogen atom. And what happens is, if these atoms share an electron, they both, in a sense, feel like they have 2 electrons in their valence shell. They feel like the 1s orbital is shared. And that's sort of the rules for covalent bonding. Any electrons that are shared get to be counted in the valence shell of each atom doing the sharing. So I see this hydrogen atom gets to count both these electrons, and it feels like it has 2 in its valence shell. This hydrogen atom gets to do the same thing because they're cooperating, and so it feels like it has these 2 electrons in its valence shell, and both of them have a filled first shell, and they're both very satisfied. And so what we see here is this connection, this sharing of electrons. We call that a covalent bond. It's actually a chemical bond, and this is the basis for hydrogen being a diatomic gas. If a hydrogen atom shares an electron with another hydrogen atom, it's in a sense satisfied, and what we end up with is an H2 molecule, a packet of matter that sticks together through a covalent bond. We can also see this, say, in the the molecule fluorine. So if I'm going to look at fluorine, I can draw 2 fluorine atoms, both with 1, 2, 3, 4, 5, 6, 7 valence electrons. Let me do that here. Here's this fluorine atom with 7 valence electrons. Here's another fluorine atom with 7 valence electrons. I'm going to go ahead and draw the electronic configuration for both fluorine atoms. So that's going to be 1s, 2, 2s, 2, 2p, 5. 1s, 1, 2, 2s, 1, 2, 2p, 1, 2, 3, 4, 5. Of course, we're going to do that for the other fluorine atom, like that. And we see if these two atoms share electrons, we can kind of then make it look like that entire second shell now, because the second shell only contains the 2s and the 2p, the entire n equals 2 shell is full. And therefore, this particular fluorine atom and this particular fluorine atom both, in a sense, feel satisfied, and they are connected by this single chemical bond. So we can sometimes just draw it like this, or as you saw, we write the formula just F2. This is why fluorine is a diatomic molecule. Another way to think about this is both fluorine atoms want to gain one electron. I mean, this is a simpler way of thinking about it. Both fluorine atoms want to gain a single electron so as to gain the same electronic configuration as the nearest noble gas. And that's essentially going to be true of all of these particular halogens. They all want to gain one electron to achieve the electronic configuration of the nearest noble gas. You might guess that oxygen is going to want to gain 2 electrons, and nitrogen and those in its family are going to want to gain 3 electrons, and importantly, carbon tends to gain 1, 2, 3, 4 electrons. So these are the atoms that tend to, actually it's the nonmetals, that tend to want to gain electrons, so they tend to receive electrons or share them so as to gain the configuration of the nearest noble gas. It also turns out that what we often find as atoms gain and share electrons, they do so as to gain what's called a stable octet. A stable octet of valence electrons. And when they gain this stable octet of valence electrons, they tend to achieve the configuration of the nearest noble gas. So let's just look here at fluorine. If we count every electron that's being shared, so 1, 2, 3, 4, 5, 6, 7, 8. Sure enough, there's a stable octet in this valence shell, and for this fluorine, we see the same thing, 1, 2, 3, 4, 5, 6, 7, 8. Now, this stable octet of valence electrons is very useful in describing how atoms come together to form bonds, but don't get too used to it because this is kind of like a guide, but not a law. Atoms are often looking to achieve what we call a stable octet, but in many ways, this achieving a stable octet is often violated. So this is sometimes called the Octet Rule. The Octet Rule, which is many, but not all atoms, share electrons until they achieve a stable octet. In order to achieve the stable noble gas configuration. We already saw how this played out in the fluorine molecule. Let's see how it might play out in the chlorine molecule. So if we look at chlorine, we notice that it is indeed a halogen, and all halogens have 7 valence electrons, 1, 2, 3, 4, 5, 6, 7. So if I was going to draw the Lewis dot symbol for chlorine, I'd draw its symbol with 8 X's around it, with 7 X's around it. I'm going to do that for 2 different chlorine atoms. And the octet rule is a very nice guide to help me understand how the chlorine atoms combine, they bond, they share electrons, so that each chlorine atom feels like it has 8 electrons in its valence shell. 1, 2, 3, 4, 5, 6, 7, 8 for this chlorine, and likewise 8 for this chlorine. And so we can kind of see that chlorine atoms bond by sharing electrons. They bond once to form the chlorine molecule. It's interesting to see how this happens, say, in oxygen, O2. Let's see how this might work. This is a little different. So I'm going to draw my oxygen atom with 1, 2, 3, 4, 5, 6 valence electrons. Here's oxygen. 1, 2, 3, 4, 5, 6. And we'll draw another oxygen atom over here with 1, 2, 3, 4, 5, 6 valence electrons. And we see if these oxygen atoms share once, well, that's not enough, because by sharing once, this oxygen atom feels like it has 1, 2, 3, 4, 5, 6, 7 valence electrons. And of course, the same with this oxygen atom. That's not enough. We want to get to the stable octet. So what's done is those oxygen atoms share a second time. And if they share that second time, then both oxygen atoms feel like they have 8 electrons in their valence shell. 1, 2, 3, 4, 5, 6, 7, 8. Remember, you get to count electrons for both atoms. Any electrons that are shared by both atoms get to be counted by both of them. So we see O2, the oxygen atoms share twice, and this sharing twice, we call that a double bond, and sometimes we'll just draw it like this. And this gives us a basis for thinking about how two oxygen atoms share electrons in a covalent or cooperating valent bond to form the O2 molecule. Let's do the same thing with nitrogen, N2. Why does N2 exist as N2? Well, let's look here. If we're going to do the same thing for nitrogen, we recognize that nitrogen atoms have 1, 2, 3, 4, 5 valence electrons. So I'll draw those in. Nitrogen 1, 2, 3, 4, 5. And another nitrogen atom 1, 2, 3, 4, 5. So they all have these 5 valence electrons. And let's see, we're going to need to share once. That gets us to 6, right? Every time an atom shares electrons, it gains 1. So this takes me from 5 to 6 is the first sharing, to 7 in the second sharing, to 8 if it shares 3 times. So all of these electrons, the ones the atom brings to the table, so to speak, and the ones that it gains through sharing, it gets to feel like that's in its valence shell. So this nitrogen feels like it has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons, whereas this nitrogen atom gets to feel like it has 8 as well. And by cooperating with their electrons, making a covalent bond, we see that, sure enough, in nitrogen, a triple bond is formed. And that is the basis for nitrogen gas being N2. This travels around as a packet of 2 nitrogen atoms that are connected through a very strong triple bond, and this is the basis of the bonding that occurs between N nitrogen atoms in the nitrogen molecule.